Today, we're going to discuss formulas for solutions of equations of degree 3 and 4. These formulas were first published in the book by Girolamo Cardano in 1545, and the book was titled Artis Magnae, or The Great Art. Cardano's book was extremely influential at a time when algebraic notations were still emerging. In this book, we see Latin letters already used to denote various parameters, but the equations are still written in words. Also, this book contains the first use of complex numbers. The methods that we're going to discuss in this lecture are much more modern and based on Galois theory. We will begin by discussing the construction of Lagrange resolvent. The setting here is the following. So we have a Galois extension with a cyclic Galois group and suppose it has a cyclic generator sigma. And we assume that F contains a primitive mth root of 1, which we denote by zeta. Well, it's exponential of 2 pi I over m. So zeta to the power m is equal to 1. As in the previous lecture, we consider a Zm grading on the field E by eigenspaces of operator sigma. E decomposes into a direct sum of one-dimensional subspaces. So dimension of each Ej over the field F is equal to 1. The space Ej is the eigenspace for sigma, so it's x and E, such that sigma of x is equal to zeta to the power of j times x. And the space E0 is the fixed point set under the Galois group action, and by Galois correspondence, this is equal to the base field F. What we would like to do is to construct projection operators from the space E onto each of these components. Operator sigma has order m, so sigma to the power m minus identity is, of course, equal to 0. But then this expression may be factored over F as the product, k goes from 0 to m minus 1, of sigma minus zeta to the power k times identity. But we can also factor this expression over rationals. So this is sigma minus I times identity plus sigma squared plus sigma to the m minus 1. Comparing these two factorizations, so we get that identity plus sigma squared plus sigma to the m minus 1 is equal to the product from k from 1 to m minus 1 of sigma minus zeta to the power k times identity. Now, what does this operator do on each of these components? We can see that the factor sigma minus zeta to the power k times identity annihilate the space ek. So we see that operator I plus sigma squared plus sigma to the m minus 1 applied to eigenvector x will give us 0 if x belongs to Ej with j not equal to 0. And if x belongs to the component E0, then each of these operators will act as identity and we're going to get m times x, so if x belongs to E0. So if we divide this operator by m, then we will obtain a projection operator from E to E0. To construct a projection operator to component Ej, we slightly modify this construction. So we consider the product k goes from 1 to m minus 1 of zeta to the power of j times sigma minus zeta to the power of k times identity. To expand this, we substitute zeta to the power j sigma instead of sigma, and we get identity plus zeta to the power of j sigma plus zeta to the 2j sigma squared plus zeta to the m minus 1 j sigma to the m minus 1. This expression is called the Lagrange resolvent and denoted as zeta to the power of j and sigma. The product on the left will not annihilate a single component, which is E minus j. So this is because this product does not contain the term with k equals 0. So we conclude that 1 over m times Lagrange resolvent is a projection from E to the component E minus j. Next, let us study the cubic equation. By a simple change of variables, a cubic equations may be written in a depressed form. That is, without the quadratic term. So we'll write x cubed plus ax plus b is equal to 0. Our goal is to find the roots of this equation. First, we're going to look at the factorization. X cubed plus ax plus b is equal to x minus alpha 1 times x minus alpha 2 times x minus alpha 3, where alpha 1, alpha 2, and alpha 3 are possibly complex roots of this cubic polynomial. First, we write the Vieta's theorem. The sum of the roots of this equation, alpha 1 plus alpha 2 plus alpha 3, is going to be 0, because we don't have the quadratic term here. Then the coefficient a is the sum of pairwise products of the roots. So we have alpha 1 times alpha 2 plus alpha 1 times alpha 3 plus alpha 2 times alpha 3 is equal to a. And finally, the constant term is the product of the roots with a negative sign. So alpha 1 times alpha 2 times alpha 3 is equal to minus b. Here we treat the roots of this polynomial as indeterminates, and these become the values of elementary symmetric functions in alpha 1, alpha 2, and alpha 3. And the general result about symmetric polynomial tells us that any symmetric polynomial in alpha 1, alpha 2, and alpha 3 is expressible in terms of elementary symmetric polynomials. And that is in terms of our coefficients a and b. In our setting, for the ground field, we take not q, but the extension of q with the third root of unity. So q of zeta, where zeta is e to the 2 pi I over 3, or minus 1/2, plus root of 3 over 2 times I. And we let E to be the splitting field of our cubic polynomial f over k. So this means that E is an extension of k with the roots alpha 1, alpha 2, and alpha 3. The Galois group will permute the roots of this polynomial, and we assume that we are in the most general case. that the Galois group of E over K is S3. Let us consider the chain of commutator subgroups in S3. The first commutator of S3 is the alternating group A3, which has order 3, and so this is isomorphic to Z3, and the generator is a 3 cycle 1, 2, 3. This group is abelian, so the second commutator subgroup of S3 is identity. So S3 is a solvable group. Let us write down this chain. So we have S3 that contains A3, and that contains identity subgroup. And now we write down the Galois correspondence for the splitting field. So the largest subgroup corresponds to the smallest subfield, which is our base field K, so the cyclotomic field. Then here for A3 we have a corresponding subfield that we will denote by F, and so the smallest subgroup corresponds to the largest field, which will be the splitting field E. The field F is the set of elements in E that are fixed by the action of A3. So we can say that this is the fixed point set under the action of A3. And A3 is the Galois group of E over F. This tells us that the order of the extension E over F is equal to the order of this Galois group, so that is 3. And the order of E over K is the order of the Galois group of E over K, which is S3, and so that is 6. This implies that the degree of F over K is equal to 2 by multiplicativity. So F is generated over K by a single element of degree 2, and we actually know this element. Recall the construction of the discriminant. So we consider element theta, which is the product over I less than j of alpha I minus alpha j. So in the case when we have 3 variables, so this is alpha 1 minus alpha 2 times alpha 1 minus alpha 3 times alpha 2 minus alpha 3. This element is A3 invariant, but not S3 invariant. So if the Galois group is equal to S3, then we conclude that F is the extension of K with an element theta. The discriminant D is theta squared, and so it's the product alpha 1 minus alpha 2 squared times alpha 1 minus alpha 3 squared times alpha 2 minus alpha 3 squared. Now this is S3 invariant. And being a symmetric polynomial, now this is expressible in terms of our coefficients A and B using Vieta's theorem. It is a tedious but a straightforward computation to expand this and express in terms of elementary symmetric functions. And then we get that D is equal to minus 4a cubed minus 27b squared. So this is the expression for the discriminant of a cubic polynomial. And our field F is K extended with the square root of D. Now that we have the description of the field F, let us look at E as extension of the field F. The Galois group of E over F is a cyclic group of order 3, and it has a generator sigma, where sigma is a 3 cycle 1, 2, 3. We can write a Z3 grading on E. So E is a direct sum of E0 plus E1 plus E2. So here EJ is the set of X in E such that sigma applied to X is equal to zeta to the power of J times X. And the E0 component is equal to the field F, and dimension of each component as a vector space over F is equal to 1. Let us take an element alpha 1 and decompose it according to this grading. So we write that alpha 1 is P0 plus P1 plus P2, where each component Pj belongs to Ej. These components may be calculated using the Lagrange resolvent. Pj is equal to 1/3 of the resolvent zeta to the minus j with sigma applied to alpha 1. So for the component P0, we get 1/3 identity plus sigma squared applied to alpha 1, and then this becomes 1/3. So identity applied to alpha 1 is alpha 1. Then sigma is the transformation that acts by this permutation 1 to 3. So sigma applied to alpha 1 is alpha 2. And sigma squared applied to alpha 1 is alpha 3. But here, because our cubic was taken in depressed form, the sum of the roots is equal to 0. So we get that P0 is equal to 0. To get P1, we apply the operator 1/3 of identity plus zeta inverse sigma plus zeta to the negative 2 sigma squared to alpha 1, and we get 1/3 alpha 1 plus zeta squared alpha 2 plus zeta alpha 3. And similarly, P2 will be 1/3 of alpha 1 plus zeta alpha 2 plus zeta squared alpha 3. Element P1 belongs to the component E1, and element P2 lies in the component E2. Since this grading is compatible with multiplication, we conclude that P1 cubed and P2 cubed, as well as P1 times P2, will all belong to component E0, which is our field F, which is K extension with square root of D. And then we can do a straightforward but technical calculation of P1 cubed and express it in terms of A, B, and theta. And then we get the following expression, that P1 cubed is equal to minus B over 2 minus 1/2 plus zeta over 9 times square root of D. Whereas the product P1 times P2 is equal to minus A over 3. It turns out that this product is not just in F, but in K. And now we get the formulas for the roots of the cubic polynomial x cubed plus ax plus b is equal to 0. Well, alpha, the root, is equal to P0 plus P1 plus P2. P0 is equal to 0. Then P1 is the cube root of minus b over 2 minus 1/2 plus zeta is equal to root of 3 times I over 2. So we get over 18 overall times square root of D. So this is the cube root. Then P2 may be obtained from this product. So it's minus A over 3 divided by P1. So we get plus negative A over 3 divided by P1, which is the same cube root of minus B over 2 minus root of 3I over 18 times square root of D. When we compute the roots, we have to make the following choices. So we have to pick the sign when we compute the square root of D, and when we compute the cube root, we have 3 possible complex values. It turns out that by making various choices of values of these roots, we get not just the value of alpha 1, but all complex roots alpha 1, alpha 2, and alpha 3 of this cubic equation. In this denominator, we should take the same value of the cube root as we take it in the first summand. Next, let us study the quartic equation. Again, to simplify the calculations, we take the quartic equation in depressed form. So it will be x to the power 4 plus ax squared plus bx plus c. And we equate this to 0. And the first thing we do is we factor this. So it will be x minus alpha 1 times x minus alpha 2 times x minus alpha 3 times x minus alpha 4, where we treat the roots of this equation as the indeterminates. By Vieta's theorem, we have that alpha 1 plus alpha 2 plus alpha 3 plus alpha 4 is equal to 0, because again we have no cubic term here. Then pairwise products, alpha 1 times alpha 2 plus alpha 1 times alpha 3 plus alpha 1 times alpha 4 plus alpha 2 times alpha 3 plus alpha 2 times alpha 4 plus alpha 3 times alpha 4 is equal to A. Then triple products, alpha 1 times alpha 2 times alpha 3 plus alpha 1 times alpha 2 times alpha 4 plus alpha 1 times alpha 3 times alpha 4 plus alpha 2 times alpha 3 times alpha 4 is equal to minus b. And the product of the roots, alpha 1 times alpha 2 times alpha 3 times alpha 4, is equal to c. These are the values of elementary symmetric functions in alphas, and every symmetric polynomial in alphas is expressible in terms of a, b, and c. As our base field, we'll take k, which is extension of q with zeta, where zeta is again the third primitive root of unity. As we're going to see, we actually do not need the fourth primitive root of unity in these calculations. So E is going to be the splitting field of this polynomial over k. So it will be k with adjoint the roots alpha 1, alpha 2, alpha 3, and alpha 4. And we're going to assume that the Galois group is the most general. So the Galois group of E over k is S4. Let us write down the commutator series for this group. The first commutator subgroup of S4 is the alternating group A4. The second commutator subgroup is the Klein four-group V4. So V4 consists of the following elements. It's 1, 2 times 3, 4, 1, 3 times 2, 4, 1, 4 times 2, 3, and the identity. This group is isomorphic to Z2 plus Z2, and it is abelian. So this means that the third commutator subgroup of S4 is identity. If we write this chain of subgroups, so S4 contains A4, contains V4, which contains identity, then we can write the Galois correspondence. So here to the smallest subgroup we have the largest field, to the largest subgroup we have our ground field. So let us denote by F the field that corresponds to V4, and the field that will correspond to the alternating group is the extension of k with the square root of the discriminant. The indices of these subgroups will give us the degrees of these extensions. So here the index is equal to 2. So k with square root of d is the degree 2 extension of k. So here V4 has order 4 and A4 has order 12. So the index here is 3. So F is a degree 3 extension of k with square root of d. And here we have index is 4. So E is a degree 4 extension of F. The element theta is the product of I less than j from 1 to 4, so alpha I minus alpha j. This element is A4 invariant, but not S4 invariant. And if we take its square, then we're going to get an S4 invariant element. So D is theta squared, so it's the product over I less than j of alpha I minus alpha j squared. This is a symmetric function in alpha 1, alpha 2, alpha 3, and alpha 4, and thus expressible in terms of A, B, and C. The expression for the discriminant is complicated and is given by the following formula. Next, let us view E as an extension of F. The Galois group of E over F is equal to V4, and it has two generators. So that will denote sigma 1 and sigma 2. As sigma 1, we choose element 1, 2 times 3, 4. And as sigma 2, we take 1, 3 times 2, 4. We view E as a vector space over F, and here we have two commuting operators acting on E. These two operators are simultaneously diagonalizable on E, and we can write down the joint eigenspace decomposition, that E is E00 plus E10 plus E01 plus E11, where EJK is the eigenspace, so it's the set of X in E, such that sigma 1 applied to X is minus 1 to the power of j times X, and sigma 2 applied to X is minus 1 to the power of k times X. So we know that the space E00 is the fixed point set of E with respect to the group V4, so that is equal to F, and the dimension of each component EJK as a vector space over F is equal to 1. The operator of projection to the component EJK is 1/4 times identity plus minus 1 to the power of j sigma 1 times identity plus minus 1 to the power of k sigma 2. Now we take root alpha 1 of our polynomial. It's an element of E, and we can write its decomposition with respect to this grading. So alpha 1 is equal to P00 plus P10 plus P01 plus P11. Let us compute these components. So P00 is equal to 1/4 of identity plus sigma 1 times identity plus sigma 2 applied to alpha 1. This equals to 1/4 identity plus sigma 1 times, well, identity applied to alpha 1 is alpha 1, and sigma 2, which is this permutation, applied to alpha 1 will give us alpha 3. So we get alpha 1 plus alpha 3. And we get 1/4. So when we apply identity to this, we get alpha 1 plus alpha 3. And when we apply sigma 1 to alpha 1, well, sigma 1 is 1, 2, and 3, 4. So we'll get alpha 2. And alpha 3 is transformed into alpha 4 by sigma 1. And we see that the result of this calculation is 0, because by Vieta's theorem, the sum of the roots of an equation in depressed form is equal to 0. Likewise, if we calculate P10, then we'll get 1/4 alpha 1 minus alpha 2 plus alpha 3 minus alpha 4. P01 is 1/4 alpha 1 plus alpha 2 minus alpha 3 minus alpha 4. And P11 is 1/4 of alpha 1 minus alpha 2 minus alpha 3 plus alpha 4. So what we have here is that pjk belongs to the component ejk. Because this grading is compatible with multiplication, we conclude that p10 squared, p01 squared, and p11 squared, as well as the product p10 times p01 times p11, all belong to the component E00, which is the field F. So this tells us that these components of alpha are square roots of something from F. Since the sum of the roots is equal to 0, we can write that negative alpha 4 is equal to alpha 1 plus alpha 2 plus alpha 3, and then these expressions may be further simplified as 1/2 alpha 1 plus alpha 3, 1/2 alpha 1 plus alpha 2, and minus 1/2 alpha 3 plus alpha 4. It turns out that the product p01 times p10 times p11 is not just in F, but in K, and is equal to minus b over 8. Next, we consider the degree 3 extension of k of square root of d to F. The Galois group here is the quotient of A4 by V4, which is isomorphic to Z3. And we will denote the generator of this group by tau, and tau we can take to be the 3-cycle 1, 2, 3. This means that A4 is the union of cosets of V4 with respect to tau. A4 is equal to V4 union with tau times V4 and union with tau squared times V4. Next, we consider Z3 grading on the space F by eigenspaces of tau. So we write F is F0 plus F1 plus F2, where F0 is k with square root of d, and dimension of each Fj over F0 is equal to 1. The projection to the space Fk is given by a Lagrange resolvent. So it will be 1/3 Lagrange resolvent of zeta to the power of minus k with tau. And let us denote by Rijk the projection of the element Pij squared, since we know that the squares of Pij's are elements of F. It turns out that projections to the 0 component, F0, of P10, P01, and P11 squared are the same. So we have that R100 is equal to R010 and is equal to R110 and equals to 1/12 of alpha 1 plus alpha 2 squared plus alpha 1 plus alpha 3 squared plus alpha 2 plus alpha 3 squared. And it turns out that this expression is S4 invariant and is equal to minus a over 6. There are also relations between other components of these elements. So we have that R101 is zeta times R011 and is zeta squared R111, and R102 is zeta squared R012 and is equal to zeta times R112. So all we have to compute now is the components R101 and R102. These elements belong to components F1 and F2 respectively, and so their cubes will belong to F, as well as their product. So we have R101 cubed and R102 cubed belongs to F0, which is K with square root of D, whereas the product R101 times R102 in fact belongs to the ground field and is equal to A squared over 144 plus C over 12. So all we need now is to compute the value of R101, and then R012 can be expressed from this formula. We can compute the cube of the resolvent R101, and we get the following expression, and we see that the result is indeed in K with square root of D. Now we can put everything together and get the expression for the roots of the quartic equation. So we get that the root alpha is equal to P10 plus P01 plus P11, where P10 is the square root of R1010 plus R101 plus R102. So P10 is equal to the square root of R100 is minus A over 6. Then R101 is the cube root of Q. And the second component is obtained from this formula here. So we get S over cube root of Q. So this is the expression for P10. The expression for P01 is also a square root of minus A over 6 plus zeta squared cube root of Q. And Q is given by this complicated expression plus zeta times S over the same value of cube root of Q. And finally, P11 is expressed from this formula. So P11 is equal to minus B over 8 divided by P01 times P10. Adding these components together, we get the expression for the root alpha of this quartic polynomial. When we carry out these calculations, we make some arbitrary choices. So here we need to make a choice for the sign of the square root of D. Then when we compute cube root of Q, we have three possibilities for choosing this complex value. And when we compute P10 and P01, there are also arbitrary choices of signs of these square roots. Altogether, we get 24 choices that corresponds to the 24 permutations in the group S4, and this allows us to express all four roots of the quartic polynomial. It is really impressive that Del Ferro, Tartaglia, Cardano, and Ferrari were able to carry out the computations of this complexity without having the proper language for algebraic computations and without the notion of complex numbers.